let's continue the let's continue the section 6.8. This time let's talk about Newton's law of cooling. Newton's law of cooling is the following. So let's copy more words. Newton's law of cooling states that the temperature of a heated object by the following the heated object decreases exponentially over time towards the temperature of the surrounding medium okay, so let's just state the law and then we use a theorem, we use example to explain the application of the law. Okay, so the idea is to discuss the temperature of certain hot object in certain cooler surrounding area. Okay, hot object in the cooler area, then the hot object, the temperature will decrease. Eventually its temperature will be equal to the temperature of the surrounding medium. Okay. The Newton's law is to describe this process and predict the temperature of this hot object. So Newton's law of cooling. The temperature U of a heated object at a given time T can be modeled by the following function. Okay, whenever you see can be modeled, definitely there's some process, there's some reason why it can be modeled. Why? That will be explained in the calculus. Technically, this section 6.8, you will study it again when you study calculus and see why you can have such a formula. Okay, but so far in the pre-calculus, we just say, okay, assume we know this formula directly. The temperature U of T is equal to capital T plus U sub 0 minus capital T times e to kt. Here this k is negative. Cooling, the temperature decreases, so k is negative. Exponential decay. Okay, so where, let's talk about those constant, where capital T is the constant temperature of the surrounding medium, U sub 0 is initial temperature of the heated object and K is a negative constant. K is a negative constant. Okay, so that's the law, and in our class we just try to see how do we apply the law and how do we do the computation. We don't discuss why we have such law. That's calculus job. Okay, so we always use example to explain how we apply this law. Example. An object is heated to 100 degrees in whatever degree Celsius. Degree Celsius, and is then allowed to cool in a room. 100 degrees Celsius is very hot. It's the boiling water has a temperature 100 degrees Celsius. It's not like this F, it's a C. Okay, and is then allowed to cool in a room whose air temperature is 30 degrees Celsius. Okay, so this sentence tells us capital T is 30 degrees. It's the area in of the surrounding medium, so the air temperature. And this 100 Celsius degree is this U sub 0. It is initial degree of this heated, it's not indeed, it's initial temperature of this heated object. Okay, so let's talk about the question. Question 1, if, okay, you see here, you already have this T and the U0. You don't know K, you don't know the T. Okay, if the temperature of the object is 80 degrees after 5 minutes, one, will its temperature be 50 degrees Celsius. Okay, so we know the condition after 5 minutes it's 80 degrees. We want to know after how many minutes the temperature is 50 degrees. It's like the half decay, half-life. Okay, I say half because 50 is half of 100, but it's not. There's no half-life in this Newton's law of cooling. There's only half-life in the radioactive decay. Okay, now let's see. We already know T is 30, U sub 0 is 100, so let's write it. So the U of T is 30 plus 100 minus 30 is 70, e to kT. This is a formula we need. And we are going to determine this K based on this additional condition. 5 minutes, 80 degrees. So when T is 5, the temperature is 80. So we get 80 is equal to 5K. So T is 5, you get 80. So subtract 30, you get 50, 70 e to 5k. So it's 5 over 7 is e to 5k. So natural log of 5 over 7 is 5k. So k is 1 over 5. Natural log 5. 1 over 5. Natural log 5 over 7. Okay, this is k. We just use a condition to determine k. And then we're going to determine the moment when the temperature is 50 degrees. Okay, with the k, the u of t is 30 plus 70 e to 1 over 5 natural log of 5 over 7 times t. The whole thing is a coefficient. And this is a negative number because 5 over 7 is less than 1. So it's negative. Okay, then you want 50 degrees. So u is 50. U is 50, 30, 70, e 1 over 5. Natural log 5 over 7 times t. We don't know the t. Here we don't know the k, remember? So it's 20, 70, e 1 over 5, natural log 5 over 7 times t. And then we divide it by 70. We get 2 over 7 is e 1 over 5, natural log 5 over 7 times t. And compute the natural log 2 over 7, 1 over 5, natural log 5 over 7 times t. So we move this 5 to the other side. 5 natural log 2 over 5, natural log 5 over 7 times t. Divided by natural log 5 over 7. So t is the numerator. It's a complex. It's 5 natural log 2 over 7. This is numerator. Denominator, natural log 5 over 7. And this is the answer. Don't simplify it. You cannot use calculator. Okay, so just plug in it and write it clearly so that you don't copy anything wrong. Okay, so with the calculator, with the calculator in the real life, it's about 18.6 minutes. After 18.6 minutes, the degree becomes 50. Okay, so you just plug in the data, and you may be given the initial temperature of the heated object and the temperature of the surrounding area. What you need to do is to determine K and find the T, or have T to determine K. It's a question A. Question B, determine the elapsed time before the temperature of the object is 35 degrees. Well, determine the elapsed time. It's still the same question. Find the time so that the temperature is 35. Okay, so you just let 50. You just replace this 50 by 35. Of course, we still use the same condition. After 5 minutes, you have 80 degrees. Okay. Let's drop this degree symbol. E 1 over 5 natural log 5 over 7 and times t. You just repeat this whole process. What's the difference? Difference here is 50. Now it's 35. So the difference is not 20. It's 5. And divide by 70. 5 over 70. What is 5 over 70? It's 1 over 14. Okay, 14 times 5 is 70. And we compute the natural log. multiplied by 5 and divided by the coefficient. T is this is the answer. Be careful. This is the answer. And in the real life, it's approximately 39.2 minutes. After 39.2 minutes, the temperature drops to 35 degrees. Third question, what do you notice about the temperature as time passes? Well, this is a very this is a very subjective question. What do you notice? You can say whatever answers. It just say as the time passes, the temperature will drops and eventually approach to 30 degrees. There's no standard answer, so I'm not going to put this type of question in the exam. Okay, so we just say this T increases, the temperature decreases, and it approaches to the temperature of the surrounding medium, and that's it. Well, basically, it's just want you to feel that the object, this heated object, will eventually have temperature 30 degrees, and that process will take forever. It will never, you say, after 2 hours or 3 hours, the temperature will be 30. That's not correct. It will take infinite time to make the heated object reach the temperature of the heated object to reach the temperature of the surrounding area, surrounding medium. It will take forever. But this question is not the question in the exam. Okay. Okay, so that is the Newton's law of cooling. Newton's law of cooling. This formula is important. T plus U sub 0 minus T times E to KT. K is negative. Okay? Keep this in mind and understand how do we get K and find the corresponding T. Okay, another model. Logistic model. Logistic model is the adjustment of the uninhabited growth model. Uninhabited growth model, you see here. For example, it is growth bacteria. If it is growth, we know that exponential function will approach infinity. So technically, if you take time forever, the number of the bacteria will be infinity. But that's not the case. The reason is that, for example, when we talk about the bacteria, we always place them in some container, in certain container. In certain container, in this area, there's certain limit for the number of the bacteria. You cannot have infinitely many bacteria here. There's certain capacity. It has capacity. One at the very beginning, if you have just one or two bacteria, you don't see the capacity because capacity is much bigger than it. You have sufficient, you have enough room for you to grow. But when you already have almost a full container, then your growth will be limited, will be controlled because of this limited supplement. Okay, so the uninhabited growth model can only tell you the number of the bacteria in the early stage. In the very early stage, when you don't need to consider this carrying capacity, you can use uninhabited growth model. This is only in the early stage, but eventually you have to consider this carrying capacity. Okay, you have to consider carrying capacity. When you consider this carrying capacity, the formula, the growth model is not like this. It's called the logistic model. Okay. Why you have a logistic model in the following form? That's what will be answered. That will be answered in calculus. We don't answer that why you have such thing. We just say assume we already know this. So in a logistic model, the population P after the time t is given by the function P of t is equal to C over 1 plus A e to negative, what's that word? bt, negative bt. Okay, and where A, B, and C are constant. A, B, and C are constant. With A greater than 0, C greater than 0. Okay, AC are always positive. A and C are always positive. The model is a growth model if B is greater than 0. The model is a decay model if B is negative, less than 0. Okay, so assume we have such logistic model. You will get explanation in a calculus. Okay. c over 1 plus a times e to negative bt. And here this number c, the numerator, c is called the carrying capacity. C is the carrying capacity. Okay, so if we can sketch the graph, we will have something like this. So originally, it looks like in the early stage, it looks like this uninhabited growth model. It's exponential function. At 0, it's population is 0. Here, when we talk about abstract function, this t, of course, can be positive, can be negative. But when we talk about the real model, real problem, t is always positive. So you ignore this negative part. But when we sketch the graph of the whole function, we also sketch the negative part. And this is c. This is a half of c. When you reach the half of c, this point, half of c, it has a corresponding time. It's called the inflection point. Inflection point is always a point with a half of a capacity. And then past the half capacity, it will look like this. And it will never exceed this capacity because that's the maximum number of the bacteria this model can, this container can carry. So that's why it's called the capacity, right? Okay, so this is a growth. When this b is greater than 0, it will be like, the graph will be more or less like this. When you have the decay case, it looks like this. It's also half of c, this is c. When the point has a height half of c, is also called the inflection point. Okay, this is a logistic model. For both cases, b is negative, it's decreasing. For both cases, the graph cannot exceed the c, the horizontal point c. Okay, so let's just, based on the given graph, let's talk about the properties. The properties of the logistic model. Okay, logistic model has the following property. 1, the domain is negative infinity to positive infinity. We only mention this equation. We don't talk about the real world. The real world, of course, the time has no negative, but for this function, it's negative infinity to positive infinity. The range is between 0 and the c. It's always bounded by them. Try to see if you can read the words or not. Okay. Second, you see, it does not intersect x-axis, but it will intersect y-axis at 0 p of 0. It's always, if it intersects the y-axis, it's always 0 p of 0, 0 f of 0. Okay, so no x-intercept. Y-intercept is p of 0. Y-intercept is just y coordinates, p of 0. 3. There are two horizontal asymptotes. Y equal to 0, y equal to c are horizontal asymptotes. There are two horizontal asymptotes, 0 and c. Y equal to 0, y equal to c. therefore, when b is greater than 0, p is increasing. B is less than 0, p is decreasing. 5, that's a way we call it growth decay. 5, there is an inflection point. Inflection point where P of t is equal to 1/2 of the capacity. So what is the inflection point? Inflection point is the following. On two sides of inflection point, one curve is curved upward, the other curve is curved downward. So here you see on the left side the curve is downward, on the right side curve is upward. So this the opening, actually you can also call it opening. The opening changes. This is an inflection point. This is also inflection point. Okay. We will later in the calculus you will see how the definition of inflection point is. But here let's just explain it. The inflection point is the point on the graph where the graph changes from being curved upward to curved downward or okay, this is upward downward for the growth function. So for the growth function, for this case, it will be changed from upward to downward. And the point where the graph changes from being curved downward to curved upward for decay function. Okay, so that's the property, and there's one more property. So this is an inflection point. The last property is that the graph is smooth and continuous, no corner, no gaps. The graph is smooth and continuous. No corners, no gaps. Okay. So those are the 6 properties. 6 properties of this logistic model. And keep in mind the logistic model is a little bit complex than the growth model, uninhabited growth model, because we have to consider the environment. The environment is fixed, the carrying capacity is fixed. So you have to get certain limit, like the cap. It cannot exceed that carrying capacity. Okay, So let's try to use example to understand the application of this logistic model. So fruit flying. Fruit flies are placed in a half pint milk bottle with a banana and yeast plant. Suppose that the fruit fly population after T days is given by P of T is equal to 230 over 1 plus 56.5 e to negative 0.37t. 370. Okay. So we place some fruit flies in this environment. We are going to study its population. Okay. Let's check. Question 1. State the carrying capacity. State the carrying capacity and the growth rate. Okay. Carrying capacity, C. C is the carrying capacity. So C is a carrying capacity. And the growth rate, be careful, in this formula, B has negative sign. It's a negative BT. Negative BT. So this negative sign is not part of B. It naturally has a negative sign. Okay, so the B is 0.37. This is a growth rate. It's a positive number, so the population of fruit flies grow. Okay, increases. It's a growth rate. Determine the initial population. Determine the initial population. Initial population P of 0. Initial population is always P of 0, so it's 230 over 1 plus T is equal to 0. Exponential function is 0, so it's just 56.5, 230 over 1 plus 56.5. If you do the computation, there are 4. So initially, 4 fruit flies are placed in this bottle. Okay, 4 fruit flies are placed in the bottle. Okay, and third, what is the population after 5 days. What's the population after 5 days? Well, after 5 days, P of 5. 230 plus 1, 230 over 1 plus 56.5 e to negative 0.37 times 5. What's this? It's a 1, negative 1 point, negative 1.85. Again, in the exam, this is the answer. Don't estimate it. You do not have a calculator. Don't estimate. So, in the real life, if you estimate, it's approximately 23 fruit fly. So initially you have 4 fruit flies, and after 5 days it becomes a 23 fruit flies. Okay. How long does it take for the population to reach 180? So we know the population, we're looking for the corresponding time. Okay, just let 180 be 230 over 1 plus 6.5 e to negative 0.37 times t. Well, we're going to solve this equation. How do we solve this equation? A is, not A, let's use different word. U is V over W, U is V over W, then W is V over U, right? You exchange this quotient and the divisor. So we get 1 plus 56.5 e to negative 0.37 t is equal to 230 over 180, 23 over 18. We move 1 to the other side. It is 21 over 18 minus 1 is 5 over 18. And divide by 56.5. Okay, just computed what is 18 times 56.5. 56.5 times 18. Okay, it's equal to 5 over 1017. Okay, and then we calculate the natural logarithmic function. And divide by negative 0.7. And that's it. Actually, you don't have to really compute 18 times 56.5. You just copy it here. It's also okay. Okay, so you can write either this way or you write it this way. Either works. They're both correct answer. But you can never use calculate to approximate it. That is not the correct answer. Okay? So with the calculator, of course, it is not a difficult job. You can estimate. The value is like 14.4. So after 14.4 days, the population of fruit flies will be about 180. Right? So that's his example. Okay, let's see next example. So we have there's a name EFISCEN, wood product model. Classifies wood products according to their lifespan. Okay, so there's some classification: short, medium, long, and long. And there's a story here. You can read the book. This is example 6 on page 483. After you read the book, you will see the logistic model is given. I try to save time to finish this. Okay, so anyway, after certain words, read your textbook. After certain words, this formula is given. This formula is given. The P of T is equal to this C over 1 plus A times e to negative BT. Okay, then let's just discuss a question. See, how do we read the data from this given formula? What is the decay rate? So why here they use decay? Because remember, once again, in the formula, the power is e to negative bt. Here there's no negative sign. You have to put a negative. So b is equal to negative 0.0581. Okay, so in this part, you have to really write it like e to negative 0.0581 times t. So this is a b. Because in the formula there is a negative sign. You must generate this negative sign, and then you can determine the right b. And that's the reason it's called the decay rate, because b is negative. Okay, and second, what is the percentage of the remaining wood product after 10 years? After 10 years, you just let t be 10. You compute it. You compute a p of 10. You plug in here, you will get some expression. That's not difficult. Okay, what is the percentage? You get it, you get the percentage. And this p represents certain percentage. It's from the problem. You read the problem, you get it. And c, how long does it take for the percentage to reach 50%? Well, to reach 50% means the P of T is equal to 50. So left hand side is 50. And then you are looking for the solution of this equation for T. You're going to go through the similar process like the previous problem. Like this problem, you can find the T. Okay, so these two examples just tells us how you may see the questions for the logistic problems, because we don't discuss these logistic problems in detail. Why we have such formula? This formula is more complex, right? It's not like the unhibernate growth rate, growth model, or unhibernate growth model. It's not like that one. That one we can still explain a little bit, but this one we cannot because it requires a calculus. So if we cannot explain it, we don't give a very complex problem. We just try to ask you to be able to read the information from the formulas. What is C, what is a B, and stuff. Okay, and you can compute the corresponding time or corresponding population or the percentage or whatever. Okay, do your exercise, send me email if you have questions, and you will see some problems in the second exam or maybe in the final exam. Okay, we finish this video. We will start a new video with a new section. Thank you.